Okay, so many weeks ago we were doing Reed-Solomon code. So this was the decoding algorithm, and in the code the encoding was just so you have this big N many bits that Alice wants to send to Bob, and so you break it into blocks of b bits, and there are k many blocks, so b times k is equal to n, and each block b bit you see as a finite field element, right, a finite field of size 2 raised to b. So it naturally is a finite field element, and there are k elements, so you get a degree k minus 1 polynomial. It's a non-monic polynomial, although that thing is not very important, but in degree k minus 1 you need k coefficients, so the message gives you that, and that defines a polynomial px. You send evaluations of this polynomial. Usually in applications it is assumed that you will send all possible evaluations. Okay, so 2 raised to b is the finite field size. You will evaluate your polynomial at each field element, and you will send these 2 raised to b values. So that is small n. Okay, so you send n finite field elements, which is basically the polynomial evaluated at all the points, and then arbitrarily this information will get corrupted in the channel, and up to some limit, I mean if the number of errors is below the threshold, then the decoding algorithm will still be able to recover p and hence the message. So any questions? So you can set the parameters. From the decoding algorithm we got error tolerance nearly n by 2. Okay, small n is the number of values sent, and if the error is less than n by 2, less than half of them get corrupted, still it will work. Okay, which is a very surprising fact, because n by 2 is the theoretical limit. Okay, and your algorithm is actually able to correct nearly up to the theoretical limit. And today we will actually even cross this theoretical limit, and we will be able to correct errors beyond n by 2. Okay, which sounds impossible, but it's doable. But anyway, so here we set the parameters, and okay, so begin is the main parameter, which is it's a single parameter setting. That is the number of values sent on the channel. The key is the number of coefficients, so that is just a little bit smaller. So the stretch here is very small. The stretch is only from n by log n to n. Okay, it's minimal stretch, while the brute force would have required n square. And the field size is also around n. 2 raised to b is also around n. Okay, and for that error tolerance t is this n by 2 times nearly 1. As n tends to infinity, this is nearly 1, so this is nearly n by 2. So 50% error correction in the finite field alphabet. So alphabet here is not 0, 1, but finite field, so the element we are counting as one extended bit of information. Yeah, we did not go into the details, but all this can be done in nearly linear time in n. Okay, the evaluations and then the decoding etc. is quite fast. Okay, so with that we'll move forward. So there is one concept here, underlying concept of distance in this code and in general in error correcting codes. So for example, if in the previous slide this t, that was error tolerance of the code, 2t plus 1 is called the distance. So in our case, you have only seen one example of Reed-Solomon code. Distance of that is 2t plus 1, t as before. This is called distance because combinatorially, if you look at two code words, they are sufficiently far away in the space, which means that even if the code word which was sent on the channel, even if there is a corruption which is within a neighborhood of the code, from that corrupted string, the decoding algorithm will give you the center of the ball, which is the code word, and hence the message. Okay, so the balls around code words, they are kind of non-overlapping, and you can say their radius is t. How do we define?
The spheres around the.
Right. So it is the minimum Hamming distance between any two distinct code words. So in a picture, if you have a ball around a code word C1 and around the code word C2. So code word is a string of letters, where in our case the alphabet is finite field element. So C1 is basically this big and many field elements, and C2 is another array of big and many field elements. So in how many locations are they different? Okay, so in this alphabet, that is what we are calling Hamming distance. Usually it is for binary strings, but the same thing you can generalize to any alphabet. So C1, C2 are basically two arrays equal length, and in what is the difference? How many locations are there where the arrays are different? That is called Hamming distance between C1, C2 in this alphabet, in the finite field alphabet, and over all the pairs of code words, pick the minimum. Okay, minimize over all pairs of C1, C2. C1 different from C2, of course. So that is called basically distance of a code. Yes.
So is the distance then twice the whatever error you are decoding?
Yeah. So whatever is your
diameter of this ball plus 1.
Yeah, whatever is the requirement in practice, you want to tolerate, let's say, t many errors, then it is clear that the distance between these two arrays has to be more than 2t, strictly bigger than 2t. Even if it is 2t, you might be in a situation where t errors happen, and then that will correspond, that corrupted the corrupted code word will correspond to two balls, and then you cannot distinguish how did it arise, what was the message. So the balls really have to be non-overlapping, right? So whatever is your desired error tolerance, distance has to be strictly twice as big. So that is it. So if you have now when this code word C1 is sent on the channel, then this might shift to this position, C1 prime, right? And C2, when sent over a corrupt channel, erroneous channel, it may shift here, C2 prime. So it might shift here, and this might shift here. So C1 may actually shift closer to the ball C2, around C2, and C2 may shift closer to the ball around C1. So they are getting very close, and if these two balls were actually, there was an overlapping point, that point then you will not be able to decode, because it will correspond to two code words. But in this case, it's okay, because the nearest code word to C1 prime is still C1, right? So that is actually the advantage that Bob has. No matter what the channel does within the threshold of t or less, Bob will able to always get to C1 from C1 prime. And this radius is t, of course, of the balls. Okay, so up to t errors, these corrupt strings will remain inside the ball. Any questions? So this is the notion of distance of a code word, of a coding scheme, in fact, in general. It is clear that you cannot cross 50%, you cannot even achieve 50%. So distance delta implies that error tolerance of any code word, of any coding scheme, is less than delta by 2. Right? So if you have a mathematical coding scheme with a proven distance of delta or less, then in practice the error tolerance will be less than half. It cannot be better than this. So distance can be, in terms of fractions, it can be at most 1, and so the error is always, tolerance is always less than half. Okay. So what in particular what it means is, with the error bound, so if there are half or more errors, the problem that is happening in decoding is that there are more than one possible code words and hence messages corresponding to what Bob received. There are many messages corresponding to a corrupted code word. So there are two things now. So we basically want to cross this barrier of n/2. So what if the channel makes corruption more than 50%, right? So theoretically then it is impossible to find the message, but how many messages are possible corresponding to the string that Bob received, right? So if you can count, if you can give a upper bound on the count, then there will be hope that maybe there is a decoding algorithm that gives a list of messages. Okay, so that is called list decoding. That did not exist before. Even the concept actually came with the list decoding of Reed-Solomon code, which we'll see now. Okay, and so that amazing algorithm will also give an upper bound on the number of messages corresponding to the corrupted string that Bob got. Okay, so it is both an algorithm and a combinatorial result, because otherwise it is not clear how will you count the number of code words corresponding to a string which is heavily corrupted. So the corruption is, let's say, more than 55%. So in that case, how many messages are possible? So the algorithm will not only upper bound the number of such messages, it will also give them to you in the form of a list. So could we find all of them? That's the algorithmic question. So in particular, is the list small? If the list, for example, is exponentially long, then there is no point finding them, which will happen at some point, right? If the errors are very close to how much? Yeah, so in the extreme case, if every bit has been flipped, almost everything has been flipped, then obviously you expect the messages to be 2 raised to n many. The list will be around 2 raised to n. But what if that has not happened? What if you are still very close to n/2, somewhere between 50% and 55%? So in that case, is the list still exponentially large? Right. So those are the questions of how is the asymptotic growing? Because below 50% it was just 1. So intuitively, beyond 50% it should be slightly bigger than 1, but not exponential, not 2 raised to n. So that was achieved by a theoretical computer scientist called Madhusudan. Fairly recently. So he found an efficient way to list decode. Okay, so even this term was a first. So in particular, list decode Reed-Solomon. So this is what we'll see now. So we'll do list decoding for Reed-Solomon. So okay, the setting is as before. So just to recall, so you had Alice had a message D0 to dk minus 1. These are the k field elements. The Reed-Solomon coding algorithm gave her n field elements, which is basically the evaluation. So P is the polynomial that this message defines, and the evaluation of that at E0. E0 is the kind of the first field element, then E1 is the second, and so on. So compute all these values and just send it over the channel. The channel will corrupt it. And we'll assume that at least T many are correct, greater than big T many. So greater than T are correct. And the remaining n minus big T maybe are in fact incorrect. They have been corrupted. So what Bob gets is, we are calling it C0 prime to Cn minus 1 prime. Okay, so in this only T positions are correct, and obviously Bob has no idea which big T many positions are these. There is no way to find that a priori, right? Because the number of positions is n choose T, which is exponentially large. And moreover, we will not restrict big T to be half. So the correct ones may be less than n by 2. Right, so this is a very difficult problem for Bob. So how will you solve it? How will Bob try to find the list of all possible messages D0 to dk minus 1 for some bound on big T? So you fix some bound on big T, let's say just below n by 2, and within that bound, how many messages are possible? Right, that's the question. So the way we decoded before, the unique decoding, that was by, so there was this auxiliary polynomial, right, error locator polynomial. So what was that? It collected the wrong positions, right? So it was a univariate polynomial whose roots were supposed to be the wrong positions. So now what is done is something quite different. So now we'll actually, error locator polynomial we'll pick will be bivariate. Okay, so that the idea will be that if the channel was error free, then for field element E, the value would have been P of E. So the bivariate polynomial will try to interpolate these points. Okay, field element comma P of that element. So that is a point in the 2D space, and the bivariate polynomial will interpolate that. But obviously that is not what is happening in the channel. So the channel will not really correspond to P of E for n minus T many places. But anyways, we will build and see what to deduce. So let us first change the error locator polynomial. So So, we are changing the definition. So, consider a bivariate error locator q x comma y of degree dx and dy. These are the individual degrees. So, let me define it. So, dx is the degree of q with respect to x and dy is degree of q with respect to y. Okay, so, we call these individual degrees. So, now the error locator polynomial will be very different from what we used before. First of all, it is bivariate, and in the definition you won't even see anything to do with errors actually. So, we will fix dx and dy later. Let us first develop the setting such that what we want is q of Ej comma Cj prime, we want it to be 0. Yeah, so this is just a curve that passes through all these points that Bob has received. Right? So, Bob has received Ej comma Cj prime. So, this is just kind of the curve that fits whatever Bob received. So, you do not really see what errors is it capturing, right? The definition is very different from what you saw before. Okay, so, for what conditions on dx and dy will this q exist? That also we have to remember. It will not exist for every dx dy, right? So, intuitively this q will exist only when dx and dy are sufficiently large. If one of these is very small, then this low degree q will not be able to fit all the points. So, exactly the bound you get is this. So, as long as dx, essentially dx times dy, the product of these two is at least n, q will exist. Why is that? So, how many unknowns are there in q? It's this 1 plus dx times 1 plus dy. It's a bivariate polynomial of these respective individual degrees. So, that many unknowns, and clearly in those unknowns this system is a linear system. So, if as long as the unknowns are more than the constraints. Also observe that this is a homogeneous linear system, right. So, there is no question of infeasibility. So, just by numbers how many unknowns are there, you are guaranteed a solution. So, this essentially dx times dy should be at least n, and then q definitely exists. In fact, many q's may exist. Then such a non-zero q exists. And it can be computed quite easily. By linear algebra. Right, so it exists and it can be found easily. So, Bob does that. We have still not fixed dx and dy, that will, because dx dy will put more constraints and then we will solve it. Okay, so Bob now has computed this q. How do you think this q will help? Do you see that this q hides the message or contains the message or the list of messages in fact? all possible messages are somehow contained in this queue. So to see that, let us look at the idealized setting when the channel doesn't make a mistake or doesn't corrupt. So that would have been, so let's say you look at this univariate polynomial, which is by setting y equal to px, right? So a message p of our interest, if the channel was correct, then it would have given x comma px. Bob would have received x comma px. So if you substitute that in Q, let's call that polynomial R. So do you see that this or how can you ensure that the Q that Bob has found vanishes at y equal to px? Right, this is exactly what you want. So this bivariate polynomial Q just computed in step 1, what if its factors give you y minus p's for all p's? Right, so basically Bob will then find Q and then factorize it, and the factors will give the list of messages, or in fact first P is the message. So Bob will have the list of messages. But for that Bob has to make sure that the Q that has been computed actually vanishes at y equal to p. So this R should be 0, right? Can that be achieved? Can that be ensured? So let us see the degree of this. So degree is dx of q plus, in y you have substituted p whose degree was k minus 1, right? So k minus 1 times dy. That is the degree of R. So obviously we have to use the fact that at least t many EJs are correct, right? So R at those EJs is 0. So we know that R at least some of the EJs does vanish. For t many j in 0 to n minus 1. Right, this is the hypothesis. We still haven't fixed t, we have not fixed dx, dy, t, we will do that in the end, but some guarantee has been provided that t many positions are correct.
So why this is happening?
Sorry?
R of EJ is equals to 0.
Yeah, so what is EJ comma PEJ? PEJ for those j's is CJ prime, and the Q that Bob has found satisfies that. This follows from equation 1, from this equation. So from that equation, REJ you can see is Q at EJ comma PEJ, but PEJ is the value that Bob received. So by construction of Q, this is true. So for t many values, R is vanishing, but you actually want R to vanish for all the values, for all j. I mean, okay, not really, or you want just R to vanish, right? So what matters is what is the degree of R. So we have to compare this vanishing of R at some EJs with the degree of R. So, if the degree of R is less than this, then R vanishes, right? That's the, so the last check that you have to do is compare this number t with the degree of R. So,
Sir, but in the first equation, we have assumed that it vanishes for all those 0 to n minus 1, not just for t.
sorry,
In first equation we assume that it vanishes for all.
that is fine. I mean, how is that in contradiction with, in conflict with the fact that R e j is equal to 0 for t many j? We are just using part of the construction of Q. So, so the point being made here is that as long as t is bigger than the degree is actually smaller than this bound dx plus k minus 1 dy. So, as long as t is bigger than dx plus k minus 1 dy, right, which is greater than or equal to degree of R, what can you deduce? That R is 0. And if R is 0, then you would have deduced that y minus p is a factor of Q, right, which is what Bob wants, that the factors of Q should contain P, because Bob can use enough algebra and come up with a factorization algorithm. You haven't seen how to factor bivariates, you have only seen how to factor univariates. But as promised in this course, you will see factorization algorithms for any number of variables. So, Bob can use one of those algorithms, factor Q, and hence find P. And not only one P, but all possible P's. Moreover, since Q has limited degree, there are few P's, right? So, this algebraic route is giving you a very interesting combinatorial fact, right, that the number of such strings that could get corrupted and reach Bob is small.
What is capital?
That's the message. That's the P of x, right? That was the settings we had before. P is the polynomial you get from DIs. So, P is DI xi. Okay. That's the original message. You want to find the message P. And since it is not unique, you want to find all of them. So right now we haven't fixed anything. So t is free, dx is free, dy is free. So you just set them appropriately. And for that setting, you have an algorithm. Any questions? So there are, so there is this constraint. Essentially, dx times dy should be at least n, and there is the other constraint that dx plus k dy should be less than t. These are opposite constraints. So you have to be just careful to satisfy these opposite constraints. And for that setting of t dx dy, you have a working algorithm, list decoding algorithm. So let us collect that in a lemma. So if n is less than the product and the sum is less than t. So product should be large and sum should be small, right? If that happens, then actually any curve fitting the points that Bob got. This has y minus px as a factor. Okay, so factorization is the way to go. Okay, Bob will just do linear algebra, use a system linear system solver, and then a factorization algorithm, and that will give the whole list. Okay, so this is it's a first and it's an amazing algorithm. So yeah, so the list decoding algorithm, let's see, with some parameters fixed. So let's fix you can see that you want the product large and the sum small. So why not take essentially them to be square root of n, around square root, right? So that is why we'll fix something close to square root. So let's fix dx to be square root of nk, dy to be square root of n by k, and t to be twice square root of nk. Okay, so square roots appear. You can see that dx times dy is more than n by design, and dx plus k dy is smaller than t, smaller than twice square root of nk, right? So those two constraints are satisfied. So you can apply the lemma. I mean, obviously, the square root this may not be an integer, so you will just take floor or ceiling. Simply compute q. Such that q ej cj prime is 0 for all j, and the degree bounds for q, individual degree bounds, are dx dy, right? That is the setting. And then third is factorize. There's bivariate, which you don't know how to factorize right now, but assuming some factorization algorithm, factorize this and collect its factors of the form y minus px. So essentially factors that are individual degree 1 with respect to y and monic. Okay, so these special factors, you collect them. Let me use different fx, y minus fx. Is there any property on f? Any property of f that you want to satisfy? How was your message like? Yeah, so if the factor has f with degree more than k minus 1, then it's not a message. So there is no point keeping that in your list, in Bob's list. So these factors with degree of f less than k, right? So you collect these, and this is your list of messages f. So how many are they? What is the upper bound?
dx by
Uh, it is linear in y, so dy.
or dx by k, which is equal.
dy is which is square root of n by k.
Yeah, but like you are calculating that by degree of y, right?
Yes.
You can also look at degree of x, and that will be dx by k, because each factor would have a degree k.
dx by k is also square root of n by k.
Yeah.
It's the same, but like you can also say
yeah.
it's dx. It's the minimum of dx by k and dy.
Right. So we can say in the end square root of n by k. That's sure. So number of f's is less than equal to individual degree of y, which is less than equal to square root of n by k. Right. So you get a very precise bound, which is incredible. That yeah. So let us interpret this. I don't think you have interpreted the parameters. What do they physically mean? So if you want to send a message with k field elements by stretching it to n field elements over the channel, where the channel will at least preserve square root of nk many locations or field elements correct, right? So in that case, the number of possible messages corresponding to a corrupted string that Bob received, number of possible messages is at most square root of n by k. Okay, you get a very precise bound for this setting. So how many errors are being tolerated? So that is just n minus 2 square root of nk. So even in the presence of those many errors, which is actually quite large, if you think of k as much smaller than n, in that case n minus square root of nk is nearly close to everything which is n. Right? It's not really 55%, it's more like 99%. For setting of k, you can actually make it 99% of the field elements have been corrupted by the channel. Right? Only 1% correct information is there, but still a list of all the possible messages will be outputted by this algorithm. Right. But then k has to be suitably small. So basically what it means, smaller k for the same n means that you need slightly more stretch, that's all. But the stretch that you need is only by a constant factor, right? So for a constant factor stretch of the message, you can go up to 99% errors, right? This seems theoretically impossible. Okay. So you just output these, that's the final step. So output the list. F as above. That's the list which is output. Okay. Any questions about this algorithm? So for n equal to k log square k, so basically k is being stretched to k log square k, which is not really constant factor. Why did I say constant factor? Okay, no, this I think will achieve more. So for this we only need two k log k correct values. Okay, so k is stretched to k log square k but amongst these k log square k which were sent over the channel, you only need k log k values to be correct, right, which is actually if you look at the fraction, this is tending to 0, right. So you really want you just need for this algorithm to work, to give a small list, the density of correct values is nearly 0. It's not even a constant, right. That's a even more stunning setting. Is this clear? But the stretch here is non-constant. It's k to k times log square. Okay. Yeah, so what you have in the end is, let's collect everything. So this list decoding algorithm is in randomized polynomial time. Well, we haven't shown that completely because of this major missing algorithm to factor q x comma y, but that will be our goal from now. So in the next many lectures we will see how to factorize bivariates. Basically we will reduce bivariates to univariates and then use Cantor's Zassonos. So everything will be ultimately randomized polytime, and it works up to n minus 2 square root nk many errors. And the list which it will output is very small, square root of n by k. So definitely smaller than n. Yeah, so for this these things to work, now we have to solve some new problems, right. So what are the new problems that arise out of this in computational algebra? So in decoding RS codes, we require two new algebraic algorithms. So first is construction of a finite field itself. In particular, it is f2 raised to b. So we happily said that the encoding algorithm will pick a field and then do the encoding. But since b is really a variable, how will the algorithm find this finite field or construct this explicitly? So till now you have done many exercises on finite fields, so you certainly know that they exist. And the question boils down to finding an irreducible polynomial of degree b. But how do you find it? In the application of this encoding algorithm, actually 2 raised to b is not large. 2 raised to b is only as big as n. So you can also do this by brute force, because the number of irreducible polynomials, the space is only n. So you can just try setting all possible values 0, 1. But the bigger question is, suppose b is given to you in the input. So then 2 raised to b is exponentially large in terms of b. So you cannot do brute force. You cannot go over all the polynomials of degree b. Basically, the space is too big. So how do you pinpoint one irreducible out of all polynomials? Right? Any ideas? In the first assignment, there was this question where you constructed or you saw how to construct irreducibles over Q. So integral irreducibles, rational irreducibles, that there was an explicit example, right? But for finite field, you never saw an explicit example that you can just pick. So this actually is an algorithmic problem. You have to, for every input, you have to do some computations and come up with an irreducible polynomial. So that we will see next. That's the first problem. The second problem that has arisen is a much bigger problem, which is factoring a bivariate polynomial. In fact, if you think about it, given a bivariate polynomial, you currently don't have any idea how to check whether it's reducible or irreducible. Right? Forget about factorization. Even a bivariate, how do you check its irreducibility? Right? That seems to be a very challenging question. So we'll solve all those problems at a later point. Well, so what is the easiest thing that comes to your mind to search in this exponential space of polynomials? You already know the keyword.
You can take a polynomial, factor it.
No, so you pick a random polynomial.
Yeah, pick a random polynomial and factor it.
So that is enough.
But why is it carrying the reducible factor won't be necessarily on like the required degree?
No. Even better, I'm saying that pick a random polynomial,
Yeah.
it's already irreducible. It's a one-line algorithm. Now, if you want to see why it works, well, that is of course hard. So that is what we'll do now. Why should such a thing work? So constructing FQ in general. Where Q is P raised to B. This is given in binary. In the input. Right, so in the input size is B log P. So this is simply a number, it is just given to you in the input. And for this number, you have to construct that sized field, finite field. Right, that's the input output description. You could do it by brute force, but then the time you will spend is Q. And since the input is given in binary, Q is exponentially large. When B crosses 50, then this number is actually more than 2 raised to 50, and that then becomes very quickly it becomes infeasible to actually go over all degree B polynomials with coefficients 0 to p minus 1. Right, that is truly an exponential space. As B grows, basically you want to construct an irreducible polynomial over Fp of degree B. So this construction of a finite field is completely equivalent to this irreducible polynomial construction. there is no difference in between these two problems. That you can see by the exercises on finite field. So finite field will always correspond to an irreducible polynomial. That is the way to represent it. An irreducible polynomial will immediately give you a finite field. Okay, these two questions are one and the same, also computationally. So what we will show is the random choice works. So random choice will work only if the density of irreducibles is quite high in this space of polynomials, right? So this is basically counting the number of irreducible polynomials. So we'll basically give you we'll estimate the number of irreducible polynomials of degree b over fp. So have you seen this calculation before? This is sometimes done in discrete maths course.
It uses Mobius function.
Yes. So for the exact one it does, but I will not need Mobius function. I just want an estimate. So I'll approximate everything. What it will use, the starting point is there is this magical polynomial that you have seen before that collects all the irreducible polynomials, right? So already the irreducible polynomials are collected in one place, which is this essentially x to the q minus x. So this contains degree b irreducible polynomials, but also some lower degree ones. And using the recursive structure there, we'll get a recursion, which will give us an estimate on the number. Okay, so that Frobenius polynomial is the reason why all this works. Again, so let pi L be the number of irreducible polynomials in Fpx of degree L. Now recall that x raised to p raised to L minus x has as factors all irreducibles of degree what? Dividing L, right? That is what we deduced before in Cantor-Zassanos analysis or somewhere. So L, but also the factors of L, all those irreducibles, when you multiply them, you exactly get x to the p to the L minus x, right? This is without repetition. They are uniquely dividing with multiplicity 1. So all irreducibles of degree, I want a name, k dividing L. So let us write this as a formula. P to the L is equal to what? P to the L is the degree of this polynomial. It is equal to pi k, where k divides L, and degree k irreducible has degree k, right? So and their number is pi k. So this is k times pi k, right? So k times pi k for all k, their sum is equal to the degree of this Frobenius polynomial. Is that okay? Okay, so just based on this, we'll prove a major property that pi L is between, or let me give it as a density. So, density the density of irreducibles amongst all polynomials of degree L is at most 1 by L and 1 by at least 1 by 2L. So, this is a brilliant result for many reasons. One is that it actually is an algebraic version of the prime number theorem. Right. So, prime number theorem also says that the density of prime numbers below x is around 1 over log x. And what is log in this? The analog of log here is L. Right. So, here also it is saying that it is 1 by L. So, algebra and number theory are not so different, but algebra is easier. Right. That is what you will see. So, this thing has a very short proof. On the other hand, the original prime number theorem has a very involved proof. Yeah, this can be written also in a more precise way. So, but that we do not need for the algorithm. Time is up. So, in fact, you can say that pi L is p raised to L by L. That is the main term plus square root of this. Okay, so this second thing is very precise. It is actually giving you the asymptotic behavior of pi L. The main term is p raised to L by L. The error term is square root of that. So, its error term is significantly smaller than the main term. Now, if you look at the analog of this for prime numbers, that is still an open question. Okay, whether the prime number theorem, the error term can be made square root. That is an open question for around 2 centuries. It is called the Riemann hypothesis. Okay, so, in one paragraph we can prove Riemann hypothesis here, but not in the prime number, actual prime numbers.
Prime numbers is the left hand side inequality valid? I mean 1 by 2L, 1 by
Yeah, it is some constant. Yeah, if you look at the best results, even this must be true.
Probably that requires L to be sufficiently large.
Yeah, so this is true for all L. The prime number estimate you need then bigger and bigger x. I remember definitely this on the right side a factor of 2 and on the left a factor of half will work in the prime number case. Okay, so we will start this next time. It's a short proof. It just follows the recursive formula we have written above. Okay, the above can be seen as a relationship between pi L and things smaller than L, like L by 2, L by 3. So, it is a recursive formula. If you use that recursive formula carefully, you can prove this theorem. It is quite easy. Okay.